This is section 4.6 on applied optimization. So these are going to be word problems. Most times we'll draw a picture, we'll come up with equations, and we will end up taking derivatives if we need to do that. So this little strategy box, read the problem, read it till you understand it. That just kind of makes sense. What is the unknown quantity to be optimized? We're talking max or min. Draw a picture, label anything that's important, introduce variables, write an equation for the unknown quantity. If you can, express it as a function of a single variable or two equations and two unknowns. That may require considerable manipulation. Test the critical points and endpoints in the domain of the unknown. Use what you know about the shape of the function's graph. Use first and second derivatives to find critical points, and then you should be good. All right, so the main equation is the one you want to optimize, either the max or min. Sometimes a second equation used to write the main one in terms of one variable. In this example, an open top box is to be made by cutting small congruent squares from the corners of a 12 by 12 sheet of tin and bending up the sides. How large should those squares be cut from the corners to make the box hold as much as possible? So hold it, how much, what are we looking for? We're looking for the volume. We want it to hold as much as we can. So when you draw the picture of the sheet of tin, we know it's a 12 by 12, but we're going to be cutting out congruent squares. So these little squares in here are the same. And we're just going to call them X. So X has to fall between, it's got to be bigger than 0. Why does it have to be less than 6? Well, if it's 6, you put 6 here and 6 here, you've negated the sheet. You've taken out everything. So you have a domain restriction. X has to fall between 0 and 6. And then if you think about the box after it's folded up, this is 12 minus 2x because you took these two out. You folded up this piece. This is 12 minus 2x. And this depth is x. So main equation, volume equals length times width times height. So L is 12 minus 2x, W is 12 minus 2x, H is x. That way we have everything in terms of x. So volume is the three of those things multiplied together. You do need to go ahead and multiply, FOIL that, and get that out to here. This is your volume function. Take the derivative of it, which is 144 minus 96x plus 12x squared. And we go ahead and set that equal to 0. If you notice that 12 will go into all these numbers, you can divide the 12 out first. And so if you divide the 12 out, you've got x squared minus 8x plus 12 equals 0. This will factor. You have a minus 6 and a minus 2. That will give you a minus 8 there, and we'll multiply to give you 12. So you end up with x is 6 and x is 2. Remember, we had that domain restriction. So the x equals 6 is discarded. And so our x equals 2 is our critical point. I did not put the testing of it to make sure that that was the max, because we were looking for the max, remember? But you would do that, and I did f of 2, plugged it into the original, and you got 128. That's your max value. And f of 6 would give you 0. I just showed you that. But the boxes the squares should be 2-inch squares in order to get the max value for the volume, which is 128. And I think in our question, how large should the squares be? And I don't even know if it would ask for the volume, but we found that the squares should be 2. So let's go look at our problems. We have 4 of these to do. All right, number 1, a rectangle is constructed with its base on the x-axis and 2 of its vertices on the parabola y equals 121 minus x squared. what are the dimensions of the rectangle that has the maximum area, and what is the area? So they want to know the dimensions of the rectangle and what is the area. Well, the parabola, as I've drawn the picture here, the parabola is y equals 121 minus x squared. And this rectangle is, we assume, it's equal on both sides. So this is an x value, this is an x value. So this is the width, the length, and y is the height or length of the rectangle. This is the length, I'm sorry, this would be the width. So if you know that A is L times W, you've got 2x times y, but y is equal to 121 minus x squared. So now we can have everything in terms of x. So A is 242x minus 2x cubed. Take the derivative and you get 242 minus 6x squared. Set that equal to 0. Let's solve that for x squared is 40.333. And then take the square root. X is 6.350. So, and this says round to 2 decimal places. I think I have 1. I don't know what I did there, but 2 times that would be 12.70 if you needed to put 2 places. So the long side would be, well, that's actually the shorter side. So that's going to be 12.70. And then y equals 121 minus x squared, and this is x squared, so we can put 40.333 there. So y is 80.68. That would go there. The area, you multiply those two things and you get this. All right, let's look at number 2. A rectangular plot of farmland is going to be bounded on one side by the river and the other 3 sides by a single strand electric fence. You have 1,400 meters of wire at your disposal. What's the largest area you can enclose, and what are the dimensions? Okay, so the area for this, if we know that this is a rectangle, these opposite sides are equal. So that's an x, that's an x. You had 1,400 meters of wire. So this side, using up the 2x, is 1,400 minus 2x. The area, length times width, multiply those out, take the derivative, set it equal to 0, and so you've got 4 dividing into 1,400, that is 350 is your x value. And here is where I checked it. I didn't do that on the first one, but this is what we should do, is just to verify that that is a max. And then the length is 1,400 minus 2 of those, so that'll be 700. So your dimensions, the length of the shorter side is 350, and the length of the longer side is 700, and the maximum area is 245,000 if you multiply those together. So that would get number 2. All right, let's look at number 3. You are designing a rectangular poster to contain 64 square inches of printing. It's going to have a 4-inch margin at the top and bottom and a 1-inch margin on each side. What dimensions will minimize the amount of paper used? So this time we're looking for a minimum. All right, so when you draw the picture, it does help if you draw it and you know you've got a 4-inch margin here and here, and we've got 1 on the sides. So as far as if we let this be x, this would be x minus 2. This would be y minus, that has a 6 there instead of an 8. Let me fix that. Had to do another program to get that going there. All right, so now we've got y minus 8 there. So we know that the area that we're talking about is in here. This is where the printing is. So A equals x times y. Our x is actually x minus 2, our y is y minus 8, and that total area that we are limited in is 64. So 64 equals that. Well, let's get that in terms of y. So divide by x minus 2, and then add 8. So this is what y is. Now, over here, I did the common denominator thing. I want to turn 8 into this so that it's got the same denominator. Go ahead and multiply there, get 8x minus 16. Combine the minus 16 and the 64, and you ultimately end up with this. So right here, we've got what y equals. Now I can write the area is x times that. And when you distribute that x, you've got 48x plus 8x squared over x minus 2. That is the area. We want to take the derivative of that. That's a quotient. I don't need to go through each little step there. We've been doing that for the whole course, it seems like. But you end up with the derivative is 8x squared minus 32x minus 96 over x minus 2 squared. Take that, set it equal to 0. When you multiply the denominator on the other side, it goes to 0. Factor out 8, and you've got x squared minus 4x minus 12. Divide that 8 out there, and that's gone. So you've got an x minus 6 and an x plus 2. X equals 6, x equals negative 2. We cannot have a negative. We're talking about length, and so that one's not in the domain. Your y, so your x is 6, your y would be 64 over 6 minus, yes, I'm sorry, back up here to this one. Y equals 64 over 6 minus 2 plus 8, and that would be 64 over 4, which is 14. 4 times 14. I think that's wrong. I was saying it, and it was right. It is right there. I'm tired, I think. Okay, forgive me. 64 over 4 is going to give us 16 plus 8 is 24. So your width is 6 and your height is 24. That will be, if your x is 6, okay, so those should be the dimensions. Let's look down at number 4. Two sides of a triangle are 14 and 4. Find the size of the angle theta in radians formed by the sides that will maximize the area of the triangle. So the area of a triangle, when it's not a right triangle or you don't know what it is 1/2 AB sine theta. Theta is the angle between A and B. That's a hint there. So here's our picture. A is 14, B is 4, here is theta. The area is 1/2 AB sine theta. Plug in your A and your B, and that is 28 sine theta. A prime is 28 cosine theta. Take that and set it equal to 0. Cosine of theta is 0. Where is cosine theta 0? Theta is pi over 2. And you could check it. That does prove to be a maximum area. So that one was pretty straightforward, pi over 2. So those are 4 questions to help you with just getting used to maximizing and optimizing.